This video is brought to you by thepuzzler.com. This is session number 1 of the Puzzler's AMC 10 course. We'll be looking at counting and probability in today's session. Week number 1, counting and probability in the AMC 10. Counting and probability is one of the big 4 topics that you'll be encountering on the AMC 10 test. This goes along with number theory, algebra, and geometry. We'll look at each of these topics in subsequent weeks. In today's class, though, we'll look at different counting strategies and a lot of problems, including combinations and permutations, casework, overcounting, and combinatorial identities. We'll also look at different types of probabilities and the general way to tackle probability problems. So basically, we'll look at normal probability, we'll look at geometric probability, and then we'll also look at expected value. Let's get started. Okay, we'll start really basic, make sure that everyone is at the same level by reviewing all this stuff. Factorials. So whenever you see n followed by an exclamation sign or any number followed by an exclamation sign, it means factorials, and you'd pronounce that n factorial. N factorial basically means n times n minus 1 times n minus 2 all the way to the number 1. And this is very useful, especially in counting, because there's a lot of formulas where you need to do this, and instead of writing it out, you can just use the factorial sign. One direct application, number of ways to arrange n things in a row is n factorial. That's because you have n choices for the first thing, thing that you want to place. Then there's n minus 1 choices for the second thing, n minus 2 choices for the third thing, and so on, until you only have 1 choice left for the last thing. The number of ways to arrange n things in a circle is n minus 1 factorial, because each arrangement on a circle can be rotated in n different ways, and it'll still remain the same. So you're counting each way n times, so we divide by n, and n factorial divided by n would give us n minus 1 factorial. So that's factorials. Okay, this is one of the topics on the test that appears a lot. They're usually not that simple. You usually have to realize how to apply combinations and permutations, but you do need to know them for the test. They appear quite a lot in counting problems, and there's 2 essential formulas. So there's a number of permutations, where that means that order does matter, and we'll see what that means in a second. So number of permutations of n things taken r at a time is n factorial divided by n minus r factorial. And then the number of combinations, so that means order does not matter, of n things taken r at a time is n factorial divided by n minus r factorial, and you also divide it by r factorial. So what's the reason behind dividing by that extra r factorial? Well, let's see. In how many ways can you pick 3 balls out of 5 different colored balls? So let's try this problem. Let's say we have 5 different colors. I'll call them, we can just make up colors. Let's say color A, B, C, D, E. That's easier to write than red, orange, blue, and so on. So these are our 5 colors. Well, the first thing we have to see is, does order matter or not? If I pick A, B, and C, or if I pick B, A, and C, it's the same thing. I just need to pick 3 balls. I don't actually need to arrange the balls. So order does not matter. Okay, let's forget about our formulas that we just looked at, and let's try to solve this problem without any formulas. And then we'll see if our formula works and gives us the same answer. So this should be the combination formula. But we have 5 choices. We have 5 choices for the first one, for the first ball that we pick. Then for the second ball, we have 4 choices. And then for the third choice, we have 3 choices, right? So that gives us 60 choices. But I just said that if we pick A, B, and C, that's the same thing as picking B, A, and C. And this 5 times 4 times 3 counts A, B, and C and B, A, C as 2 different arrangements, or 2 different ways of picking the balls, which is not true. So we need to account for that. Say we pick 3 colors. Let's say we pick A, B, and C. Well, how many times are we counting A, B, and C? From factorials, we know there's 3 factorial ways of arranging A, B, and C, or 6 total ways. If there's 6 total ways of arranging A, B, and C, well, that means that we're overcounting by 6. So 60 divided by 6 gives us 10. Just quickly plugging it in our combination formula, we get 5 factorial over 3 factorial times 5 minus 3 factorial, which is 2 factorial, which gives us 5 times 4 divided by 2, because 5 times 4 times 3 factorial, and the 3 factorials cancel out, or 10. Let's look at the next one before we look at other counting topics. In how many ways can you arrange 3 donuts in a row given that you have the choices glazed, chocolate, maple, strawberry, and caramel? How many choices do we have for the first donut? 5, right? 5 toppings or 5 types of donuts, so we have 5 choices. Then for the second donut, we've already picked one of the 5, so now we only have 4 choices left. And then 3. And that's how you would do this. This would give us 20 times 3, which does give us 60. Let's use our permutation formula. So here order does matter. Picking glazed chocolate and maple is different from picking chocolate glazed and maple. So our permutation formula tells us 5 factorial over, and since we're picking 3 factorial. Or let's go back to our formula once. Let's just double check. So it'd be 5 factorial over n minus r factorial. So that would be 5 factorial over 5 minus 3 factorial. Which makes sense. That's basically what we did here. That gives us 5 factorial over 2 factorial, or 5 times 4 times 3, which is 60. Let's look at the other counting strategies that we have at our disposal. So these ones are going to be a bit longer, not as many formulas oriented with them. So K-square counting, for example. Solving counting or probability problems by calculating the different cases and then adding them together. Tends to be a bit bashy, right? It takes a lot of effort, takes a lot of work. It's very easy to make some sort of a mistake where you forget some cases. And it should only be used as a last resort for counting problems. Overcounting. So overcounting is not saying that, oh, I have 60 arrangements for my donuts. Well, I counted 70. That's not overcounting. Overcounting is strategic. Overcounting is a process of counting more than the desired amount and then just systematically correcting for overcounted elements. For example, if we go back to our earlier example right here, we had 5 times 4 times 3 equals 60. We overcounted, but then we know that we overcounted each arrangement 6 times. So we overcounted it 5 times. So we divide by 6 so that it only accounts for it once. 60 divided by 6 equals 10. So we can remove this sometimes via subtraction, but usually through division. So quick example of overcounting. How many numbers less than or equal to 100 are divisible by either 2 and or 3? Okay, how many numbers less than or equal to 100 are divisible by either 2 and or 3? So how many numbers are divisible by 2? 50. Or we can actually write it here, 100 divided by 2. So how many numbers are divisible by 2 from 1 to 100? Is 100 included? Yep, less than or equal to 100. So that's 100 over 2. And then for 3s, that's going to be 100 over 3. Well, this is not an integer. 100 over 3 is not an integer. And we're just going to round down, right? There's 33 numbers between 1 to 100 that are divisible by 3, namely 3, 6, all the way to 99. So this gives us 50. So you can actually put the floor function here if you want to be exact. But 50 plus 33, which gives us 88. But what about numbers that are divisible by both 2 and 3? We counted them once here, and then we counted them once here. So we overcounted those. We counted them twice. We only want to count them once. So we want to subtract those numbers once. Well, the numbers that are divisible by 2 and 3 are actually also divisible by 2 times 3, or 6. How many numbers are divisible by 6 from 100, from 1 to 100? 100 divided by 6, and taking the floor function of that. And we'll learn more about why this method works in a future class. So 100 divided by 6, that's 96 divided by 6 would be 16, and then plus 4, 6. So that just rounds down. So 88 minus 16 gives us 72 as our answer. So there's 72 numbers less than or equal to 100 from 1 to 100 that are divisible by 2 and or 3. And then word arrangements are also another great example of strategic overcounting. And the reason being is if you have some word, let's say we have the word good. If you had the word, say, dog, just with 3 letters, then from our factorials, we know there's 3 factorial ways of arranging this. But with good, it's not simply 4 factorial ways of arranging it, even though there's 4 letters. The O's can be switched out. So if the O's can be switched out, we're counting each arrangement twice, since in each arrangement where the O's can be switched out, they're actually the same. So if we say G01, O2, D. So O1 and O2 are actually both O's, but they're distinct O's. So if we have G, O2, O1, D, that's the same thing. So we're counting each arrangement twice. So we need to divide by 2, or more specifically 2 factorial, since the 2 O's can be arranged in 2 factorial ways. And in general, when you have a word that's, say, K letters long, then there's K factorial ways of arranging it. And then you divide by the factorial of the number of times each letter appears. So if we have a word like banana, 6 letters, so 6 factorial, divided by how many times do the A's appear? 3 times. So they can be arranged in 3 factorial ways. So each time with the A's, we're counting each of the same arrangement 6 times. So that's 3 factorial. The N's appear twice, so that would be 2 factorial. And notice how the B appears once, so that would be 1 factorial. So you don't even need to include that because anything divisible by 1 is still the same. So yeah, it would be K factorial divided by D1 factorial, D2 factorial, and so on, where these numbers correspond to how many times each distinct letter appears. Okay. Complementary counting. So this is a counting method where one counts what they don't want, then subtracts that from the total number of possibilities. It often provides a simpler approach in problems that must otherwise be bashed out, the word that we used earlier. So a large hint that complementary counting may lead to a quick solution is the phrase not or at least within a problem statement. For example, if it says at least one, how many ways can you get at least one head out of 5 heads? Well, you can just see how many ways can you get heads in total, like how many total coin flips are there, and then subtract the number of ways that you get 0 heads, and you get your number of ways. Okay, let's move on. Constructive counting. So constructive counting is a counting method where one constructs a set to count it. It's a close cousin of casework, as constructive counting usually involves breaking the problem down into several smaller counting parts. We'll see more of this when we're actually solving our AMC 10 problems. Something that also appears in the test, not directly, but applications of it, is the Pascals Triangle. And this triangle, you start out with 1, and then below that, there's always 1 on the edges, and any number is the sum of the numbers right above it, right? So 56 is the sum of 35 and 21. And the cool thing about this is you can rewrite all the terms in Pascal's triangle this way. So remember, this symbol right here, when you write something and choose k, this is combination. So this means n factorial over k factorial times n minus k factorial. And you can write each element like this of the Pascal's triangle, where any element is equal to, for example, row 0, your top is going to be 0, the first element is 0, the second element is 1, and so on. So that makes it quite nice for us. Even though you won't usually directly use Pascal's triangle in AMC 10 problems, here are some identities without proof that are derived from it. And these can help simplify a lot of the later AMC combination problems. So this won't really appear in the first 15 problems, but really in the last 10, these can really help you out. Especially when the point is to use these identities, it's very hard not to do it any other way. So Pascal's identity, it states that n choose k is equal to n minus 1 choose k minus 1 plus n minus 1 choose k. And then the hockey stick identity says that n plus 1 choose k plus 1 is equal to n choose k plus n minus 1 choose k plus n minus 2 choose k, all the way to k plus 1 choose k plus k choose k. Okay. One more identity that is a bit more obvious, but that's quite helpful, is n choose k is equal to n, choose n minus k. And we can prove this, we can attempt to prove this by using it and plugging it into the formula. So the first one becomes n factorial over k factorial times n minus k factorial. And this is equal to n factorial over n minus k factorial times n minus n plus k factorial. And this is just k factorial. So then n factorial on both sides, k factorial on both sides, and n minus k factorial on both sides. So they're the same. So that's the proof for that. Okay, we're done with the main theory part for the counting problems. We didn't do too much theory, but that's still more than enough. Let's actually look at some AMC problems to see how we're going to be seeing this in the actual test. One note about the problems is that we'll be starting out relatively easy. I think this is a number 12 from the 2004 AMC 10 test, but we'll quickly move on to very hard problems. So if you think this is easy, this is not the end of what we're going to be covering in the video. We'll be moving on to numbers 24, number 25 from the AMC 10 test. So hold on to that part of the video. And if you think this is hard, well, that's what we're here for. We're going to work through this together and get you to the level where you can solve number 24 and number 25, or the last 5 on the AMC 10 test. So 2004 AMC 10. Henry's Hamburger Haven offers its hamburgers with the following condiments: ketchup, mustard, mayo, tomato, lettuce, pickles, cheese, and onions. So just quickly counting, we see 8 condiments. So I'm going to just write that here. 1, 2, 3, 4, 5, 6, 8 condiments. A customer can choose 1, 2, or 3 meat patties and any collection of condiments. How many different kinds of hamburgers can be ordered? So there's 2 different things that we have to look at here. First, how many patties they have, and any collection of condiments. So how many possible collections of condiments are there? So first, they have 3 choices for the patty: 1, 2, or 3. So if they're vegetarian, they're out of luck. There's no choice for 0 patties. So that's 3 patties. And then out of the 8, there's any collection of condiments. So in their burger, they can either have ketchup or not have ketchup. They could either have mayo or not have mayo. They could either have pickles or not have pickles. For each individual condiment, there's 2 choices: either have it or not have it. So that's 2 times 2 times 2, 8 times, or 2 to the power of 8. That's 3 times 2, 56, or 768. Notice that we didn't actually go over this in the theory part, but using the tricks that we learned, using the basic theory, we know that we can basically construct the set this way and look at what we need to do to figure out this problem. There's not always going to be a specific way to do them. You do need to explore them, and that's how you're going to solve them. So 2019 AMC 10A. A child builds towers using identically shaped cubes of different color. How many different towers with a height 8 cubes can the child build with 2 red cubes, 3 blue cubes, and 4 green cubes? So 1 cube will be left out. Okay, let's see. So we have 8 cubes, but we have 9 cubes, right? So we have 9 total cubes, and we only want 8 of the cubes. And the problem tells us that you can just count 2 plus 3 plus 4 equals 9, but it does also tell us that 1 cube will be left out. Okay, so first we have to pick what cube are we going to leave out. There's 3 different cases. We could leave out a red cube, a blue cube, or we could maybe leave out one of the 4 green cubes. So that would give us, let's say we leave out the red cube. Then we have 1 red cube, 3 blue cubes, and 4 green cubes. And we need to find the number of ways to arrange this. This is R, B, 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 G, 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 right? And we're just asked to find the number of ways to arrange this. But we remember from our word arrangements, the number of ways to arrange this is 8 factorial, because that's how many letters there are, divided by the factorial of the number of times each letter appears. R appears 1, so it doesn't matter. B appears 3 times, and G appears 4 times, right? So we made this from the blocks to a word rearrangement problem. So this gives us 8 factorial over 3 factorial times 4 factorial. That's going to be 5 times 6 times 7 times 8 over 3 times 2 times 1. 3 times 2 cancels out here. And we're left with 35 times 8 which is 70 times 4, or 280. Okay, what about if we leave out the blue? We leave out the blue, we'll be left with 2 reds, 2 blues, and 4 greens. So same thing, 8 factorial. This time we divide by 2 factorial, 2 factorial, and 4 factorial. Doesn't change much though. We're left with 5 times 6 times 7 times 8. And this time instead of 3 times 2, we're going to do 2 times 2. 2 cancels out here and here. So we're left with 35 times 12, which is 350 plus 70. Notice how I'm trying to do the arithmetic in the easiest possible way for us to solve the problem. 420. Okay, now we need to look at our last case, which is when the g cube is excluded. So that's going to give us with 2 reds, leave us with 3 blues, and 3 greens. So 8 factorial over 2 factorial, 3 factorial, and 3 factorial. So let's move down. This is 8 times 7 times 6 times 5 times 4 over 2 factorial, and then one of the 3 factorials also canceled out, so we're left with 3 factorial. So 3 factorial cancels out with the 6, 2 factorial cancels out with the 4, giving us a 2 here, and we're left with 56. So 56 times 10, or 560. That's it. Those are the only 3 cases we have. So 560 plus 420 plus 280, that's 900 plus 200, or 1100, plus 460 plus 20 is 80 plus 80. That gives us 1260. Let's check if that's a choice, and sure enough it is. So our answer is D. But wait, I told you guys that earlier casework should be left as the last resort. Maybe there's a better way to do this problem. This problem seemed to take a lot of time, and it's easy for us to make some arithmetic mistake here. Let's delete all this. Okay, so how else could we do this problem? There must be another way to do this problem, right? Well, there's a few things that we could do. Let's delete all this. How many cubes do we have initially? Let's write them out. So we have 2 red cubes. Then we have 3 blue cubes. And 4 green cubes. So this arrangement of cubes, what if we just let the last cube be the letter that is going to be tossed out? And then just find the total arrangements of this 9-letter word, and then the last cube just represents what we have. So then we have 9 factorial. The first letter appears twice, so 2 factorial over 3 factorial. And then G appears 4 factorial. So this is 9 times 8 times 7 times 6 times 5 times over 2 times 3 times 2. So 3 times 2 cancels out here, 2 cancels out here, and we're left with 9 times 7 is 63 times 20, which is 630 times 2, or sure enough, that's also 1260. So you could have just arranged this as one word, and the last letter just represents the letter being tossed out. So there's always and usually a better way, not always, but there's usually a better way to do the problem than casework. Let's move on. A license plate in a certain state consists of 4 digits, not necessarily distinct, and 2 letters, also not necessarily distinct. These 6 characters may appear in any order except that the 2 letters must appear next to each other. How many distinct license plates are possible? Okay, so let's pick the 4 digits first, not necessarily distinct, that's 10 to the power of 4, because we have 10 choices for each letter, and then 2 letters, that's 26 squared. Now we have to find the number of ways to arrange them such that the 2 letters must appear next to each other. Well, that's pretty limited. Either the 2 letters appear in the first and second place, or the second and third place, or the third and fourth, or the fourth and fifth, or the fifth and sixth. That's only 5 choices. So we multiply by 5, And that's it. 10 to the power 4 times 26 squared times 5, and sure enough, C matches our answer. And that's it. You don't need to overthink that one. We move on. How many rearrangements of A, B, C, D are there in which no two adjacent letters are also adjacent letters in the alphabet? For example, no such rearrangements could include either AB or BA. Looking at this problem, I don't really see a quick way to do it. So let's play around with it a bit. Let's see. I mean, the answer choices look pretty limited, 0 to 4, so maybe there's not that many. We can't have A, B, or C, D. So let's say we start with A. If the first letter is A, maybe this is a casework problem where we need the first letter to start with A. Then the second letter, it can either be a C, in which case the third letter is not allowed to be a B or D, but then we have no choice. There's no choice for the third letter, so it can't be C, so it needs to be D. And then this next letter can't be C, so it needs to be B. And then once again, C can't go next to B, so that doesn't work. What if we have B, then A or C can't go here, so D needs to go here. Then C or A, only A can go here, and then C. This works. That's one. It's not A. Then just by symmetry, we know that there's going to be one that also falls from C, but let's double check. So C, only possible choice is A, then D, then B. So that's another. So we have 2. Now, by symmetry, we know there won't be 1 in D, but let's not focus on that. Let's see if there is. D, if you have B here, then there's no choice for the third letter since A or C can't go here. And if you have A, then C, B can't go here because C and B don't work. So there's 2 choices for this one, and we're done. Okay, let's move on to the next problem. There are 10 people standing equally spaced around a circle. Each person knows exactly 3 of the other 9 people. 2 people standing next to him, or next to her or him, as well as the person directly across the circle. How many ways are there for the 10 people to split up into 5 pairs so that the members of each pair know each other? Well, it seems like they're representing some sort of a circle. Why don't we draw that circle? So, to draw a circle, we don't actually need to draw a circle. I don't even think you're allowed to bring a compass to the AMC 10. We're going to just write the numbers in a circular manner. So, person 1 is 1, 2, and so on. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. And how many people are we looking for? There's 10 people. Okay, so then we have 10. So that's close enough to a circle, as long as you guys understand. Okay, and that's actually true on the real test. As long as you understand what the problem's asking for, you'll be fine. So I don't see any way to do this problem without using some sort of casework. From what I'm seeing, we can look at how many different diameters there are and do casework on that. There doesn't seem to be any other simpler method. So on a test, you just want to go with that method. It takes 30 seconds to think about whether you can find any other method. But if you can't, just go with the method that you know. So let's look at the diameters. What if there's 0 diameters? If there's 0 diameters, then let's start with 1. 1 can either pair with 2, then 3 needs to pair with 4, 5 needs to pair with 6, so on and so on. So that's 1. So let me write it here. So if we have 0 diameters, there's 1 case. Or we can go the other way around, and that gives us another case. So that gives us 2 cases. What about if we have 1 diameter? Well, we have 5 choices to pick for the diameter, right? There's 5 different pairs, 1, 6, 2, 7, 3, 8, 5, 9, and 10, 4. So let's see. Yeah, so we have 5 choices. So let's see. Let's say we pick this one. Now we see that since there's only 1 diameter allowed in this case, 2 has to go with 3, 4 has to go with 5, 7 has to go with 8, 9 has to go with 10. So this is just 1 case. So 5 is our total number of cases since there's 5 different diameters you can pick. What if we have another diameter? So we picked 1 and 6, and then we have another diameter. So let's erase this. So we have 5 times 1 equals 5. And then we now have our second diameter, which is 1/6. And what could be our next diameter? Let's say we pick 2 and 7. If we pick 2 and 7, well, then there's 3 on each side, and there's no way to actually arrange these, right? Because if we pick 8 and 9, the 10 is going to be left alone. And if we pick 5 and 4, the 3 is going to be left alone. So you can't do that since there's only 2 diameters allowed. So let's move on. What if we pick 3 and 8? Well, if we pick 3 and 8, the 2 and the 7 are still left. The 2 and the 7, they can only be connected with a diameter, so that's not allowed. So what if we pick this and this? Well, still this 10 is going to be left over and it has no one to be with. And same thing for 10. 10 and 5, you're going to have 3 on each side. So I don't see anything with 2. What if we have 3 diagonals? We have 3 diagonals. Let's say we pick these 3. Then 4 and 5 must be together and 9 and 10 must be together. Okay. So if we pick 3 diagonals next to each other, there's only one case in that. And then we have to find the number of ways to pick 3 diagonals next to each other. What if they're not next to each other? So what if we pick 2, 7, and if we pick 5 and 10, they're going to be next to each other again. So we don't want to make them next to each other. So our only choice left is 4 and 9. We pick 4 and 9, then the 10 and the 3 and the 5, and they have no one to be with since they're not allowed to be on diameters. So the 3 triangles, when we have 3 diagonals, they must be next to each other. In how many ways can the 3 diagonals be next to each other? So you could have 1, 2, 3, 2, 3, 4, 3, 4, 5, 4, 5, 6, 5, 6, 7. But notice that 5, 6, 7 is also the same as 10, 1, 2, right? So we can start from 1, 2, 3 all the way to 10, 1, 2. So that gives us 10 cases, but 5 of them are the same since they're just the other ends of the diagonal pair. So there's 5 here. What if we have 4? So we have 3 already. Let's pick a 4th one. And we immediately notice the problem. There's going to be 2 numbers left, and they're basically not possible because they're on the other end of the diameter, and there's no more diameter slot. But we can have 5. If we have 5, we just circle all of the diameters, and that's one way. So we get 2 plus 5 plus 5 is 12 plus 1 gives us 13. So this is the type of problem where you want to do your cases carefully so that you don't miss anything. So that's our final answer. Let's move on. 2018 AMC 10B. 3 young brother-sister pairs from different families need to take a trip in a van. These 6 children will occupy the second and third rows in the van, each of which has 3 seats. To avoid disruption, siblings may not sit right next to each person in the same row, and no child may sit directly in front of his or her sibling. How many seating arrangements are possible for this trip? So looking at the choices, they're ranging from 60 to 120. So we can't really count the number of arrangements. Let's see. So there's 6 children. Let's call the siblings A1. Let's just call them A, B, C, C. So this is the first pair of siblings, second pair, and third pair. Okay, so in each pair, you can always switch around the sister and the boy where they're sitting. So we have to multiply by 2 for each of these. So 2 here, 2 here, 2 here. So at the end, I'm going to write that here. We're going to multiply by 8, right? At the end, our answer is going to be multiplied by 8. That also tells us, though, that our answer must be divisible by 8. Since the number of cases without multiplying by 8 is going to be a number, is going to be an integer, and integer times 8 is always divisible by 8. So it can't be, for example, 92, 60 is not divisible by 8, so it can't be 60, but it can be 72, 96, or 120. So if you can't solve this problem, but you've gotten that first step, you've already raised your chances of guessing the correct answer from 1/5 to 1/3. So there you go. Okay. So we have AA, BB, and CC. Let's say that A starts in the top left corner. If A starts in the top left corner, where would the other A need to go? So to avoid disruption, siblings may not sit right next to each other in the same row, and no child may sit directly in front of his or her sibling. So the second A can't go here, can't go here. What if it goes here? If it goes here, then say B goes here. Then the second B can't go here, but it can go here. And then C, C. Okay, what else do we have? We could have A, B, and then we said A here. What if we have B here? But then the two C's would be right in front of each other, so that's not allowed. Okay. So then where could the third be? Where else could B sit? What if B sits right here? B sits right here. Then we already said this case doesn't work, the one where B is in the middle. So what if B is right there? Then C and C would be like this. Right? So basically what we're noticing is that the three sibling pairs are also interchangeable. And there's 6 ways of arranging those 3 pairs, right? There's 6 ways of arranging them because A, B, and C, that's 3 letters, and that's 3 factorial 6. So we also have to multiply by 6 at the end. So our answer needs to be divisible by both 8 and 6. Or 8 times 6, which is 48. And the only numbers that are divisible by 48 are actually, well, 96. So that's our only answer left. So that would actually be your answer if you were in a time crunch. But why though? We have to actually go through the cases. Let's see if we actually get 96 as our answer. So without letting the cases be indistinguishable, so let's say brother sister X sits here and brother sister Y sits here. So then right here we could have X sit here. If X sits here, then what is our choice for here? Well, we could have Z, and if Z sits here, then what sits here? It can't be Y. X is already taken, so Z must go here. But that's not allowed, so this isn't a valid combination. So what if you have Y here? But then you would have Z and Z. That's also not allowed. So you can't have this X, Y, X combination. So this X and Y are fixed. So if you can't have a X in this third letter, maybe that's wrong. And we need to have a Z. Okay, then what can we have here? We could have a Y here. If we have a Y here, then X could fit here, but then Z is left over here, so we're not allowed to do that. So what if Z comes here, then X would come here. Okay, that's one valid combination. What if we have X, Y, Z, and then instead of Y here, we have Z here? Then X would need to come here because Z or Y can't come there. And then right here, we would have the last letter, which is Y, and that's valid. So there's 2 possible valid cases, no other valid cases. And there's 3 ways to pick what goes for X, 2 ways to pick what goes for Y, and 1 way to pick what goes for Z, like which sibling pair, A, B, or C. So that's what the times 6 was about. I hope that makes sense, but if it doesn't, please feel free to ask in the chat. So we have 2 times 6, and then we also have to multiply by 8. So 2 times 6 times 8, and like we suspected, 48 is the correct answer. Let's move on. By the way, if you still haven't subscribed to our channel or liked this video, please do make sure that you do that. We're providing this free resource, and the only thing that we're asking is you do that so that it reaches even more people and they're able to access these free resources to help excel in the AMC 10. Back to the problems. Let's try 2003 AMC 12A. How many 15-letter arrangements of 5 A's, 5 B's, and 5 C's have no A's in the first 5 letters, no B's in the next 5 letters, and no C's in the last 5 letters? I believe this is a last 5 problem from the AMC 12, so it's not meant to be easy. Okay, first of all, looking at the notation, what is this sigma? Well, don't be scared by the sigma. Basically, what that's saying is take the sum of 5, choose k, to the power of 3, and the value of k is going to be first 0, so do 5 choose 0 cubed, then it's going to be 1, then it's going to be 2, all the way to the value on the top, which is 5. So 5 choose 5 cubed. So that's all that's saying. You don't need to be scared of that notation. That's all that's saying. It's also highly likely that that probably won't be our answer and they just scared us with that. But let's see. Let me draw 15 dashes to represent our arrangements. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And let's play around with the problem. Let's say we have 2 B's here. Only 2 B's in the first 5. Well then, the other 3 letters in the first 5, they can't be A's, so they need to be C's. In the next 5, you can't have any B's, so you can only have C's and A's. And you remember that there's no C's allowed here. Since there's no C's allowed here, the C's must go in the second 5. So there's 2 C's here. And then the rest of them must be A's since there's no B's allowed. And then the remaining letters, A, and then B, 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 go here. So if you have 2 B's in the first 5, this is a possible rearrangement. And how many different rearrangements are there? Well, in the first 5, you have to pick 3 spots for the C's. Or let's say 3 spots for the B's, so if I choose 2. And then in the second 5, we have to pick 2 spots for the C's. Doesn't matter where they go as long as they're in that 5. And then the same thing for the third spot. We have 5, choose 2 for the A's. And that's when we have 2 B's. But guys, think about it. What if we have 3 B's? Does anything change? Yeah, we would just do 5 choose 3 times 5 choose 3 times 5 choose 3. What if we have 5 B's? Well, then it would just be 5 choose 1 times 5 choose 1. 5 choose 5 times 5 choose 5 times 5 choose 5. So that's just one possible way, right? B, 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 B. So B, 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 and then C, 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 and then A, 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 right? So that is basically, it's all dependent on the number of B's that we have in the first value. And that could be anything from 0 to 5. Wait a second, that's basically what this formula is saying right here. That as k switches from 0 to 5, it's just 5 choose k cubed, which is what we're looking for. So that's our answer, and we can move on. That was a hard one. Don't worry if you didn't understand something about that. And if you have any questions, please be sure to ask. This is the final counting problem that we'll do before moving on to geometry. 2003 AMC 10A. Pat is to select 6 cookies from a tray containing only chocolate chip, oatmeal, and peanut butter cookies. There are at least 6 of each of these 3 kinds of cookies on the tray. How many different assortments of 6 cookies can be selected? A 22, B 25, C 27, D 28, and E 729. Wow, that's a big number. Okay, so looking at these choices, what do we think? So she can have all 6 of, like, say, chocolate chip cookies. That is assured by the second statement right here. There are at least 6 of each of these 3 types of cookies. So we can have chocolate chip, peanut butter, or oatmeal. So you can do this problem with casework. Say you have 0 chocolate chip cookies. Order doesn't matter, right? So it's 0 chocolate chip cookies. Then you can do casework on the number of oatmeal and peanut butter. And then 1 chocolate chip cookie. Then you would have casework on oatmeal and peanut butter again, and so on. And that would actually not be too tricky. Let's look at that. Chocolate chip cookies, if there's 0 chocolate chips, and then how many oatmeals you could have. You want 6 cookies, right? So you could have anywhere from 0 to 6 oatmeal, and then the rest would be peanut butter. So if, like, for example, you have 0, then you would have 7, 6, 5, all the way to 1. So there's 7 cases here. When you have 1 chocolate chip cookie, same problem, but now it's 0 to 5, and so on. So this would be 6. So this would be 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. And that's 7 times 8 divided by 2, or 28. So that's it. That's our answer. But what if this problem had different numbers? What if the numbers were bigger? Let's look at a general method to solve these problems. This method is referred to as the stars and bars method, and we won't go into detail because I feel like it's not something that you should try to memorize. It's just you should understand how it works. We have 6 cookies, right? So let's draw 6 cookies on our plate. 1, 2, 3, 4, 5, 6. And now say I divide the cookies with 2 dividers. And I say that the number of cookies here represent the number of cookies that are that are oatmeal, no, that are chocolate chip. The number of cookies between the second two dividers represent oatmeal, and then the number of cookies, the remaining cookies at the end represent the number of peanut butter cookies. So this will always add up to 6, right? Because there's 6 total cookies or circles that I've drawn. And we just have to find the number of ways to arrange this. This is arranging 8 different things, and 6 of them are cookies, 2 of them are dividers. So 8, choose 2, right? Choosing 2 spots for the dividers. Notice that the dividers can be next to each other, which would just mean that there's 0 cookies here. So 8 choose 2 is 8 times 7 divided by 2, or like we did, 56 over 2 equals 28. And in general, this is a method that you can apply in a lot of counting problems, where you draw in the circles or something like stars representing your objects, and then you also add in the dividers, and then you can just use combinations to solve this problem. That's it though. We won't be going into more detail for that. Let's move to part 2 of our class today. And now it's giveaway time. We'll be giving away 2 Wolfram Alpha notebook editions valued at $49.95 each. To enter this giveaway, go to thepuzzler.com/amc-10-course-giveaway. You'll also find a link to this giveaway in the video description below. Don't forget to subscribe and like this video if you haven't already. You liking this video really helps us in getting an algorithm boost and getting this video out to more people so that more people can enjoy this free resource. So we'll give you about 20-ish seconds to enter the giveaway, and it's okay if you can't do it right now. You can always do it after the class. We'll be announcing the giveaway winners in next week's session. Okay, let's move on. Part 2 of today's class is going to look at probability, expected value, and geometric probability. Probability is just the number of ways an outcome can occur over a total number of outcomes possible. Sometimes people overcomplicate this and think of this more than that. You don't need to think of probability problems as more than just this simple formula, and all problems that involve probability just boil down to this formula. We'll start by looking at 3 basic examples of AMC 10 probability problems before going into harder examples. One thing you'll see is that our counting strategies fit in quite well with probability questions. Since let's go back to our formula, to find the number of ways that an outcome can occur, you need to use a lot of our counting strategies. And although it's usually easier to find the total number of outcomes possible, you still do need to use some strategies to do that. 2 different numbers are selected at random from 1, 2, 3, 4, 5, and multiplied together. What is the probability that the product is even? Okay, so 2 different numbers are selected at random from this set. There's 5 choices, right? So let's underline the set. There's 5 choices, and 5 choices for the first number, and 4 choices for the second number, and we're choosing 2 of them. So order doesn't matter, so this is just 5 choose 2, which is 5 times 4 divided by 2, or 10. So there's 10 possible choices. So our probability is going to be over 10. What is the probability that the product is even? Okay, so we're going to solve this problem. There's not that many cases, so you can just count them, but we're going to solve this problem using complementary probability. Complementary probability basically says that if you're trying to find the probability of something, if we're trying to find the probability of something, we can find the probability of some other event, say B equals 1 minus A. So we can find the probability of A not happening. So that would be B, and the probability of that is 1 minus A. So then we can do 1 minus B, which would give us 1 minus A, or the probability of A. If that sounds a bit confusing, don't worry. So basically what we're saying is that let's find the probability of A not happening, subtract that from 1, and you'll get the probability of A happening. So if A doesn't happen, that means that the product is not even. That means the product is odd, right? If a number is not even, it's odd. So a number is odd when the 2 numbers we're multiplying, both of them are odd. So for both of them to be odd, there's 3 odd numbers, and we are allowed to choose any 2 of those odd numbers. So that would be 3, let's just plug in 3, choose 2, or 3 over 10. So there's a 3 over 10 chance that the product is going to be odd. Subtract that from 1 to get the probability that the product is going to be even, or 7 over 10, which is 0.7. We can quickly just double check our work. We can have 2, 1, 2, 2. Oh, it says two different numbers. So 2, 1, 2, 3. Let's write them here just so we can keep track. 2, 1, 2, 3, 2, 4, 2, 5. Those are all even. And then we could also have 4, 1, 4, 3. We can't do 4, 2 because we already did 2, 4. And then 4, 5. That's 7 over 10, so we know we're correct. Let's move on. So that just shows how complementary probability is just simpler than using other types of strategies in probability questions sometimes. A radio program has a quiz consisting of 3 multiple choice questions, each with 3 choices. A contestant wins if he or she gets 2 or more of the questions right. The contestant answers randomly to each question. What is the probability of winning? Well, a contestant wins if he or she gets 2 or more of the questions right. Well, this is saying at least 2 questions right. And if you remember from our complementary counting part in the counting section of this video, that's usually a good sign of using complementary counting. So here we can try using complementary probability. So a contestant wins if he or she gets 2 or more of the questions right. And there's 3 choices and 3 questions. So if they get 1 or 0 questions correct, maybe we don't need to use complementary counting here. Because if we use complementary counting, we have 1 or 0 questions. And if we don't use it, then we just need to calculate the probability of 2 or 3 questions, since there's only 2 or 3 questions. So in this case, it doesn't matter. I'm going to use complementary counting because we want to get practice using that so that we always have that as an option. So a contestant wins if he or she gets 2 or more of the questions right. So probability that they get 0 questions right, well, each has 3 choices and only 1 choice is correct. So the chance that they get it wrong is 2/3 for each of them. And there's 3 questions, so 2/3 times 2/3 times 2/3, which equals 8 over 27. 1 question right, the probability of that happening is, first you have to pick which question was correct. There's 3 choices to pick. And then the probability of getting that question correct was 1/3. And for the other 2 questions, you have 2/3 times 2/3 since they must be wrong. So 3's cancel out. This gives us 4 over 9. Or I'm just going to convert it to the denominator to 27 just so we have the same denominator. So that's 12 over 27. So 8 over 27 plus 12 over 27 gives us 20 over 27. That's a chance that she gets, that the contestant gets 1 or 0 questions correct. But we're looking for 2 or more. And if they don't get 1 or 0 correct, then they got 2 or more correct. So that's 1 minus 20 over 27, which gives us 7 over 27. Let's move on. 2004 AMC 10A. Coin A is flipped 3 times and coin B is flipped 4 times. What is the probability that the number of heads obtained from flipping the 2 fair coins is the same? Okay, so this looks more like a counting problem. Well, if you have 3 coins, let's call the first set of coins here, and then the 4 coins here. What is the probability that the number of heads obtained from flipping the coins, from flipping the 2 coins is the same? So it must be the same. So what can you flip here? Let's say you have 0 heads. My initial thought is to do casework here. If we have 0 heads in both of them, well, first you have to figure out the probability. And here's something that you need to make sure you do in these type of problems. So to calculate the total probability, you have to remember that there's H or T choices at each coin. So we could have H here or T here, H here or T here, and so on. And that's 2 to the power of 7 choices. So at the end, we're going to multiply by 1 over 2 to the power of 7. So in how many ways can you have 0 heads? Well, 0 heads, out of these first 3 coins, we're asked to pick 0 places where it's going to be heads. So we have to place 0 heads. And then in the second 4 coins, so in coin B, you have to pick 0 places to have the heads. Then for 1, let's scroll down. It's going to be 3 to the power of 1, because you have to play one place to have the heads, and then 4 to the power of 1, and so on. So it's going to be 3 to the power of 2 times 4 to 4, 3 choose 2 times 4 choose 2, and then 3 choose 3 times 4 choose 3. And this isn't too hard to solve. We can actually solve this using identities, but I don't think that's necessary. We can just actually just simplify this here. We get 1, 3 times 4 equals 12. 3 choose 2 is 3, 4 choose 2 is 6, so this is 18. Then 3 choose 3 is 1, 4 choose 3 is 4, so this is 4. So we get 12 plus 18 is 30, 30 plus 4 is 34, and then 34 plus 1 is 35 over 2 to the power of 7, which is 8 times 8, 64, times 2, which is 128. So our answer is D. That's it for the basic probability, guys. Let's look at some hard probability problems now. We're now going to begin the hard probability questions of this session today. So 2003 AMC 12B. Let S be the set of the permutations of the sequence of 1, 2, 3, 4, 5, for which the first term is not 1. So we want the first term not to be 1, and then permutation tells us that order does matter. Our permutation is chosen randomly from S. The probability that the second term is 2 in lowest terms is A over B. What is A plus B? So we just can't let the first term equal 1. Okay, so then what if the first term is 3, 4, or 5? All these cases are symmetric. It doesn't change if the first one is 3, 4, or 5. So if it's 3, then the probability that the second term is going to be a 2 is, well, there's 4 choices left for the second number in the permutation, and one of them is 2, so that's just 1/4. Same thing with 4, and same thing with 5. So the chances of the first numbers being 3, 4, or 5, well, they could be either 2, 3, 4, or 5. So there's 4 choices, and 3/4 chance that we're going to pick a number from here. 3/4 times 1/4 give us 3/16. Now the first number could be 2. That's a 1/4 chance of happening. And then the second term being 2, well, that's 0 because we already picked the 2. So that's 0. So 3 over 16 is our final answer. 3 plus 16 gives us 19. So we select 19 and we're done. Not too hard, right? Let's move on. This is from the 2021 AMC 10B test. And this is one of my favorite problems. I think you guys are really going to like this problem. So a pair of 6-sided die is repeatedly rolled until an odd number appears. What is the probability that every even number appears at least once before the first occurrence of an odd number? So first occurrence of an odd number is when we stop. There's many ways to do this problem, but here's what I like the best. To give this problem a try, I'll just write out our outcomes until then. We can have a 1, a 2, a 3, a 4, a 5, or a 6, and see what you get. So how do we start off? Well, first number, we need to be even, right? We need it to be even, 3 out of 6 choices, and that's that. So first number is even. Let's say we picked a 2. Now, for the second number, we've already picked a 2. So if we roll a 2 again, that's basically, it doesn't change the number of even numbers that we have, and it's not an odd number. So it basically means nothing. So if we roll a 2, it's just a reroll. We're going to roll again and see what we get. So it's almost as if the choice for 2 doesn't even exist. We only have 5 choices left for our second roll. Because if we roll a 2, it's just a reroll. So out of these 5 choices, there's 2 even ones left, so 2 over 5. Let's say we picked a 6. Now, same thing with 2 and 6. If we roll a 2 and 6 in our third roll, well, those aren't valid. And we're just going to re-roll. And it doesn't affect anything. So we have 4 choices left then, and only one of them is even. So we have 3 times 2, which cancels out with 6. And then 1 over 5 times 1 over 4, which gives us 1 over 20. So this answer is simply 1 over 20. There's many ways to do this problem. If you think you have a different way that's even cooler, feel free to write it in the YouTube comments for this video. But I think this was probably the easiest and fastest way. Let's move on to the next problem. Let's try perhaps the hardest problem of today's session. A problem from the 2015 AMY 1. As many of you might know, AMY is the next level in the AMC 10 test. This test has completely different dynamic in its problems, and it's much more difficult from the AMC 10. So this is actually from the first 5 of the AMC 10, from the AME. So you might know that the first 5 from the AMC 10 are super easy, but from the AME, well, it's usually harder than the AMC 10. So let's try this problem. We're given 9 delegates. So 9 delegates. And they include 2 officials from Mexico, 3 officials from Canada, and 4 officials from the United States. During the opening session, 3 of the delegates fall asleep. So the 3 sleepers were determined randomly. The probability that exactly 2 of the sleepers are from the same country. So 2 of the sleepers are from the same country. So this is the number of cases we're looking for on the top of our probability, is m over n, where m and n are relatively prime positive integers. Find m plus n. So we're going to have a probability, right? The total number of ways is 9 choose 3. So we have 9 choose 3 on the bottom. Since there's 9 delegates, we can pick any 3 of them to be the one sleeping. So 9 choose 3 is 9 times 8 times 7 divided by 3 times 2 times 1. So this gives us 3 and 4 cancel out. So 3 times 4 equals 12 times 7 gives us 84. So this right here on the bottom, let's erase this. This is equal to 84. Now, how do we find the number of ways to have exactly 2 of the sleepers be from the same country? Well, there's only 3 countries. So this problem looks like it's ripe for casework. What if the 2 sleepers are from Mexico? Well, there's only 2 officials from Mexico, so picking 2 sleepers from Mexico, there's only one way to do that. Or more specifically, 2 choose 2, which is 1. And then we have to pick one of the other 7 officials. So there's 7 ways to do that, so there's 7 ways. Such that the 2 of the sleepers that are from the same country are from Mexico. What if the Canadians are sleeping? There's 2 Canadians that are sleeping. That would be 3 choose 2 ways of picking the 2 Canadians. And then for the third delegate, it can't be from Canada, so subtract those 3, and there's 9 total. So we're left with the 2 from Mexico and 4 from the United States. So that's 6. 3 choose 2, well, 3 choose 2 is equal to 3, and 3 times 6 gives us 18. So there's 18 cases right here. Okay, finally, what if the United States delegates are sleeping? Well, the United States delegates are sleeping. There's 4 of them, so 4 choose 2. And then out of the other 5 delegates, one of them is sleeping. So this gives us 4 choose 2 is 6. 6 times 5 is 30. So we have 30 plus 18, which is 48, plus 7, which is 55 over 84. 55 is divisible by 5 and 11. 84 is not divisible by 5 or 11. So we can't simplify this further. But that's not our answer. Question is asking find m plus n. So that's going to be 55 plus 84, or 130 plus 9. So 139. And that's it. We just solved an AME problem. Good job, guys. Let's move on. Okay, another hard problem. The 2009 AMC 10A. 2 cubical dice each have removable numbers 1 through 6. The 12 numbers on the 2 dice are removed, put into a bag, then drawn one at a time, and randomly attached to the faces of the cubes, 1 number to each face. The dice are then rolled and the numbers on the top 2 faces, or the 2 top faces, are added. What is the probability that the sum is 7? So I decided not to add any choices for this question because I feel like that just allows us to guess the answer. We don't want to guess this one, and we want to solve it. Good practice with the last AME question that we just did. Okay, so we have a bag. Let's draw our bag. What does our bag look like? Let's say that's a bag. This is a bag, a nice looking bag. And then we have our 2 dice, and we're taking off the numbers. The dice are distinct, so we can actually just make them distinct. Let's change up the color. So 1, 2, 3, 4, 5, 6, and the numbers from the second dice are green. 1, 2, 3, 4, 5, 6. Okay, what is this problem asking? It's saying we take 6 of these random 12 numbers. We take random 6 of these 12 numbers, put them on a die, attach the other 6 on another die, roll the 2 dice, and whatever roll on the top, find the sum. What's the probability that the sum is 7? Well, if you think about it, by symmetry, all of the rows are equally likely to come up. The the blue 1 and the green 5 is just as likely to come up as the blue 3 and the green 3, right? So all of the rows are equally likely. So that's just saying how many ways can you sum up to 7? Well, how many total rows are there? There's 12 numbers, and we can choose any two of them to represent our row. 12 choose 2 is 12 times 11 divided by 2, or 132 divided by 2, which is 66. How many ways can you sum numbers up to 7 from these 12 numbers if you pick any two? You could have 1 and 6. You could have 2 and 5. You could have 3 and 4. But for each of these arrangements, you have two options for one. You could either pick blue or you could pick green. There's two numbers for each case. Similarly, you have two options for the 6. And so on. So for each number, you have two choices. So 2 times 2 gives us 4 choices here. Similarly, 4 choices here and 4 choices here. So we have that 12 total choices work for the dice roll. So 12 over 66, that's equal to 6 over 11. And that's it. That's equal to 2 over 11. And that's it. Our answer is 2 over 11. Okay, let's move to the next and final part of our class, expected value and geometry. So geometric probability is when a problem has an infinite number of outcomes, and you can use graphs and geometric areas to find the probability of certain outcomes. So here's a basic example. A game is programmed to randomly put your character somewhere on the computer screen that has a rectangular lava pit on it. If you land in the lava pit, you lose points. The screen is 10 inches by 17 inches, and the lava pit is 2 inches by 10 inches. What is the geometric probability that you'll land in lava? So in total, there's 170 inches that you could land on. So you have to realize that the 2 inches by 10 inches, well, this is a computer screen. There's an infinite number of points on the computer screen. On any geometric shape, any 2D shape, there's going to be an infinite number of points. So we can't just use our normal total number of successful outcomes over total number of outcomes. That won't work here. So we need to flip it around a bit. What we do is 170 is the total area, and then the lava pit is 2 inches by 10 inches. So our successful area is 20. So problems like this, you have successful area over total area. So total area. And that's our new probability formula for these type of problems. It's just that simple. Let's see the applications though. So this is a simple application. Lava pit is 2 inches by 10 inches, 20, and then over 170, that gives us 2 over 17 as our answer. Before we look at some more geometric probability problems, you should know that these don't appear too often on the test, and there's usually a maximum of one problem that can be solved using geometric probability. It is very easy though. It makes problems very easy if you can use this. Before we move on though, let's look at expected value. So expected value is just the average value of a random variable over a large number of experiments. There are three main types of expected value questions: binomial random variables, multiple events, and discrete random variables. We won't go into depths here, but I do have a video on expected value on my channel that I would really suggest you check out if you're just interested in the more theoretical part of expected value. So that's a lot of abstract concepts. Let's look at the problems. So these are some basic expected value problems just to get an initial idea of how expected value works. So if a fair 6-sided die is rolled, what is the expected value of the number rolled? So to calculate this type of expected value problem, you take the outcome. So the outcome is, say, getting a 1, and then you multiply it by the probability of getting that outcome. So the probability of getting a 1 is 1/6. So 1 times 1/6, then the outcome 2 also has a 1/6 probability, and then all the way to 1/6 probability of getting a 6. So factoring out the 1/6, we have 1 plus 2 plus all the way to 6, which is 1/6 times 6 times 7 over 2, because that's the formula n times n plus 1 over 2. So we cancel here, and the average value is 7/2. And that makes sense because the expected value, you would expect it to be 1 and 6 is the lowest and largest values on a die, right? So the average of 1 and 6 is 3.5, so this makes sense. If you flip a fair coin 20 times, how many tails can you expect to get? So how many tails can I expect to get if I flip a coin once? Well, the probability of flipping tails on a coin is 1/2. If I flip it 20 times, then I can multiply each of those 1/2 expected tails, multiply by 20, and we get 20/2 equals 10. So you can notice that both of these simple questions, but different types of expected value. Let's look at the number one. Let's look at number one, but switch up the probability so that they're not all the same. So Bill Gates is considering a business investment. The investment has a 20% chance that his anticipated returns would be negative $9,000, so a loss, and an 80% chance that his anticipated returns would be $15,000. What is his expected return? So the outcome, negative $9,000, we need to multiply it by the probability that it occurs. So you can write 20% as 2/10. And then we add to that the outcome $15,000. And the probability of that happening is 8/10. The 10s cancel out, so we're left with 2 times negative 900, which is negative 1800, plus 8 times 1500, which gives us 3000 times 4, or 12,000. So 1500 times 8, that's 3000 times 4. Just double checking, that's 12,000. Yep. And then here we have negative 900 times 2, which is negative 1800. Looks correct. 12,000 minus 1800, well, that's going to be 10,200 as the expected return. So yes, if Bill Gates wants to get even richer, he should make this investment. Okay. Those were the easy problems. Let's look at an actual AMC 10A problem with expected value. So 2006 AMC 10A. A player pays $5 to play a game. A die is rolled. If the number on the die is odd, the game is lost. If the number on the die is even, the die is rolled again. In this case, the player wins if the second number matches the first and loses otherwise. How much should the player win if the game is fair? In a fair game, the probability of winning times the amount won is what the player should pay. So you don't even need to know any formulas. They tell you in that last line everything that you need to know for expected value. But let's see. So he paid $5. If the number on the die is odd, the game is lost. So he loses with one half chance on the first roll. And then if the number on the die is even, the die is rolled again. So first it needs to be even. So that's 1/2 chance of it being even. And then in the second roll, the case is that the player wins if the second number matches the first and loses otherwise. So the chance of rolling the same number on a die is 1/6, because there's one successful roll out of the 6 possible rolls. So that's 1/12 chance. In a fair game, the probability of winning times the amount won is what the player should pay. So 1/12 times X equals $5, right? This is our formula because that's what he's paying. He's paying $5. So X is equal to 12 times 5, or $60. So he should win $60 for this game to be fair. Would you take this bet? I don't know. Let's move on. Let's look at the final problem for the day. 2017 AMC 10A. This is a geometric probability problem. Chloe chooses a real number uniformly at random from the interval 0 to 2017. Independently, Laurent chooses a real number uniformly at random from the interval 0 to 4034. What is the probability that Laurent's number is greater than Chloe's number? Now you can probably just use logic to sort this problem out. And using casework like we did earlier, like we learned earlier, you could solve this problem. But I'm going to show you guys a cool way to solve this problem that's probably going to take the least amount of time, or if you can't use logic, this way is bound to work. Let's draw a coordinate plane. And then I'm going to put Chloe on the x-axis, like Chloe's number on the x-axis, and Lauren's number on the y-axis. So we have 4034, and then each tick represents 2017. Since that's what we're scaling by, no point in scaling by a number smaller than that. And then 2017. So our total region, since there's an infinite number of numbers that each of them could pick, our total region must have an infinite number of points. And yes, it does. It's a 2D shape. It's actually a rectangle. Because Lord can pick anything from 0 to 4034. That's included in this. And every xy point represents, so any xy point on the plane represents x being Chloe's number and y being Lauren's number. So that's why we draw this rectangle, because x must be less than 2017 and y must be less than 4034. So we want y to be greater than x. Let's graph that. Y is equal to greater than x. So y, let's graph y equals x. That's going to be like that. And then we want y to be greater than x. So that's not going to include this region down here. That's going to be the region above here. So that's going to be this region right here. And you can test that by trying to plug in 5, 0. That would be somewhere here. Obviously not drawn to scale. And that doesn't work, so it has to be the other side of the line. So we have this right here. What is the area of that? Well, you could try finding the area of that, but isn't it easier to just use complementary area finding? So that would be the total area is equal to 4034 over multiplied by 2017, since it's a rectangle. And the area of this rectangle is 2017, since y is equal to x, and 2017 times 2017, so 2017 squared. And then since it's a triangle, you divide by 2. And what is this probability going to be? I'm not actually multiplying out the numbers because I see everything is divisible by 2017. So this is going to be 2017 times 2017 over 2, and then you're dividing by 4034 times 2017. So 2017s cancel out, this one also cancels out, we're left with a 2, and this gives us 1 over 4. But this is the chance that y is less than x. We're looking for the chance that Lauren's number is greater than Chloe's number, which is 1 minus 1/4 or 3/4. And we're done. Thank you for attending today's session. Homework is available at thepuzzler.com/courses/AMC-10-crash-course. This is the same link that you used to sign up for the course, so you can go there to access your whole dashboard. And it consists of AMC problems containing topics that we did in class. You'll also find the handout for this week on that link. Please don't forget to give this video a like if you have not already, as it gives us a great algorithm boost. Do you have any questions? Anything about the topic material, or just any general questions? Feel free to ask it in the chat right now, or even better, ask it as a comment in this video's comment section. That way, one of our instructors will be able to get back to you with a full solution. Thank you, everyone, and see you all next week.